All right, we're beginning section 11.2, and we're going to look at probability problems that now involve the idea of not and or. So let's go through some properties of probability that we've already discussed, but let's review them again. So if E is an event within the sample space S, that is, E is a subset of S, then the following properties hold true. Remember, we said the probability of an event could be 0 or 1 or any value between. So the probability of an event is a number from 0 through 1. The probability of the empty set is equal to 0. This means the probability of an impossible event. The chances are always going to be 0 for an event that is impossible. Now, S stands for the sample space, so the probability of the sample space is always 1. This is the idea that the probability is a certain event. So the probability of a certain event is 1. So let's look at an example. When a single fair die is rolled, find the probability of each event. Well, if a single fair die is rolled, let's consider our sample space. We have 1, 2, 3, 4, 5, 6. So what would be the probability that a 2 is rolled? Well, we would say I see it once out of 6 possibilities. What would be the probability that a 7 is rolled? Well, that is an impossible event based on our sample space. So we would have 0 out of 6, which is 0. Not going to happen. How about a number other than 2 is rolled? So the probability of not 2. Well, there are 5 numbers in my list that are not 2, so my probability would be 5/6. How about a number less than 7 is rolled? Well, everything in my sample space is smaller than 7, so the probability of less than 7 is all 6 out of 6, so 1, or going to happen every time we roll. So let's get into this idea of or. So we're going to let A and B be any 2 possible events. Then the following holds true. The probability of A or B is given by the following. We're going to calculate the probability of A. We're going to calculate the probability of B. We're going to add those, and then we're going to subtract the probability of A and B. So the key question we want to ask ourselves is, are the events mutually exclusive? Two events are mutually exclusive, so events A and B are mutually exclusive events if they have no outcomes are in common. Mutually exclusive events cannot occur at the same time. So let's look at an example. Barry has 8 office assistants. If A is the event that at least 6 of them are men, and B is the event that at least 6 of them are women, are A and B mutually exclusive? The answer is yes. If Barry is going to have 8 office assistants, there's no possible way at the same time that at least 6 of them are men and at least 6 of them are women. There's no way to have both of those happening with 8 assistants. So those are mutually exclusive events. All right, so let's practice some problems involving or. For the experiment of rolling a single fair die, find the probability of the following events. You roll an even or an odd. Well, The sample space is small enough here. Let's write it down so that we can look over it. So if we roll a single fair die, we have 1 through 6 as our possible answers. When you roll a die, can you see an even and an odd number at the same time? The answer is no. So these are mutually exclusive. That means that back here, for this idea of or, there's nothing to subtract. We would subtract the probability only if they can happen at the same time. But since even or odd are disjoint ideas, we're simply going to find the probability of each and add them together. So we're going to get to do the probability of even plus the probability of odd. So the probability that you're even is how many even numbers do we have in our sample space? So 3, 6 plus 3, 6 is 6 sixths, or 1. Remember, we're still finding probability, so our answer needs to fit somewhere from 0 through 1, which it does. And it makes sense that it's 1 because when we roll a die, we're either going to get an even or an odd number every single time. All right, let's try another one. What's the probability that we see an odd number or a number less than 5? Now you got to ask yourself, can those occur at the same time? Can I see a number that's less than 5 that is odd? I sure can. So these events are not mutually exclusive. So this time we have to figure out the probability of odd plus the probability that the number's less than 5 minus the probability that you're both odd and less than 5. So let's do odd. Odd is simply how many odd numbers are in my sample space? 3. So my probability is 3 sixths. Plus, how many numbers in my sample space are less than 5? Well, I see 4. So I'm going to say 4 sixths. Now one way to check if they need something subtracted is if you stopped right here and added these fractions together, you'd get 7 sixths, which is a number greater than 1, which can't be a probability answer. So we know that these can occur at the same time, and we must do the other portion of this problem. So this says be odd and less than 5. So that's the 1 and the 3. So we get 2 sixths that we are subtracting. So if we work across, we get 5 sixths as our answer. All right, let's try some more. So for the experiment of drawing a single card, find the probability and then find the odds in favor for each of the following. So let's say that you draw a single card and it can either be a club or a heart. Well, again, the idea of or, you got to ask yourself, can those occur at the same time? Now, those are two different suits. And you either draw a club or you draw a heart. So the probability would be, what's the probability of drawing club plus what's the probability of drawing heart? Well, how many clubs are in a deck? That's a particular suit, so we would say 13 out of 52 plus 13 out of 52. We add that and get 26 out of 52. That fraction needs to be reduced, so we reduce to 1/2. Now, odds in favor is something we talked about in section 11.1, so let's review. Odds in favor would be stating the A to the B. And remember what this equals. This is A over A plus B. So it's 1 to 1. All right. What is the probability that you draw a single card and it's a club or a face card? Now, can that occur at the same time? Can you draw a face card that's a club? You can. You can draw the Jack of clubs, the Queen of clubs, or the King of clubs. So this time we need to do the probability of club plus the probability that you're a face card. I'm going to use FC for face card, minus the probability that you're both club and face card. Well, what's the probability that you draw a club? 13 out of 52. Plus, what's the probability that you draw a face card? Well, remember, there's a jack, queen, king of every suit, and there's 4 suits, so there's 12 face cards. Minus, what if we counted twice? Which cards, while only in the deck once, have we counted twice? Well, we've counted the jack, queen, and king of clubs twice, because it's a club and it's a face card. So we're going to have to subtract 3 out of 52. So when we do this, we get 22 over 52, which reduces by 2. We get 11 out of 26. Now if I want to do odds in favor, remember that's A to B, and this is A over A plus B. So A is 11. B is whatever I need to add to 11 to get to 26. So I'm going to say 15. All right, now let's look at one that's pretty simple, and let's learn not to make it difficult. So the table gives golfer Amy Donlan's probabilities of scoring in various ranges on a par 70 course. In a given round, find the probabilities of the following. Now we got to pause a minute and talk about the table. The table to the right lists all possible golf score ranges and their corresponding probabilities. The golf scores is an example of a random variable. It is random because we cannot predict which possible score will occur. This table is an example of a probability distribution. All possible scores are listed, so they make up the entire sample space. Thus, the listed probabilities must add to 1. So if I want to know what's the likelihood that Amy scores 95 or higher, I'm just going to look at any probability that corresponds to a score of 95 or higher. So I'm going to say 0.03 plus 0.01, and I'm going to get that there's a 0.04 chance that she will have a score 95 or higher. Well, what's the probability that she'll be under par? Remember they told you up here par is 70, so we want a score under 70. So we're going to look at all of those probabilities that lie with a score less than 70. So we get to take 0.04 plus 0.06 plus 0.14, and we get an answer of 0.24. How about in the 80s? Well, in the 80s, 0.09 and 0.06 correspond with scores in the 80s, so we'll add those together. 0.09 plus 0.06 equals 0.15. Now X says we're going to construct our own probability distribution table. So let X denote the product of 2 distinct numbers selected randomly from this set, 2, 3, 4, 5. And then construct the probability distribution table. So before you can do the distribution table, you need to know all of the answers you can get when the product of 2 distinct numbers happen. Well, remember, product means to multiply, and distinct means different. Now we're going to utilize from chapter 10, we're going to build a product table. So we're going to say 2, 3, 4, 5, 2, 3, 4, 5. The reason why we get to use a product table is because we're choosing 2 different numbers and then multiplying them together. Now I can't take 2 times 2, so that's an X, but I could do 6, I could do 8, I could do 10. I can do 6, I can't do 3 times 3, I can do 12, I can do 15. So remember, I'm grabbing a number from the top and a number from the side. As long as they're different, I get to multiply them together. So I get 8, I get 12, I can't do 4 times 4, and I get 20. I get 10, I get 15, I get 20, and I can't do 5 times 5. This here is building my sample space. Now for my probability distribution, if I want to make my probability distribution, it looks just like this one. I have an x side and a probability side. So I'm going to let x be any product that we found because that was our task. Let x denote the product. And then I'm going to write down, well, how many times did it happen? So what are all the different products that we got? We got a 6 from our table. We have an 8. I'm just going to put them in numerical order. 10, 12, 15, and 20. So now we want to find out, well, from our table, from our work, how many times did this happen? So the first thing that we want to count is how many total answers did we get in our table. So we have 3, 6, 9, 12. So we have 12 total answers in our table. How many times did we see 6? 2. So we'd have 2/12, or we could reduce that to 1/6. How about 8? If we notice, they're all the same. 8's in here twice, 12's in here twice, 15 and 20. They're all, so it's 2/12 or 1/6 for every single one. So this right here would be my probability distribution table. Remember how to check your work is the fractions should add to 1. So if I have 1/6, 6 times, I get an answer of 1. All right, so a couple more here with the idea of or. How about if a hospital has 8 nurses and 5 physicians, where 7 nurses and 3 physicians are female, find the probability if a staff person is selected at random, this person will be a nurse or a male. Remember, every time you see this word or, you have to ask yourself, can those occur at the same time? Can we have a nurse on staff that's male? Yes. So we're going to do the probability that someone from this hospital is a nurse, plus the probability that someone from this hospital is a male, minus the probability that you are both a male and a nurse. So we'll say that you are a male nurse. Well, first thing, how many nurses are on staff? There are 8 nurses on staff, and how many total people work at the hospital? Well, the sample space is 13 because 8 and 5 make 13 people on staff. So we're going to say 8/13. Plus, how many are male? Well, they don't ever really talk about the male, but we know that there are 10 female. 7 and 3 make 10 female. And if there are 13 in total, that must mean 3 are male. So 3 out of 13 are male. Minus, how many male nurses are there? Well, let's look at the nurses. There are 8 total nurses, of which 7 are female. So 1 must be male. So the number of male nurses is 1 out of 13. If we put this together, we get an answer of 10/13. Right, one more with this idea of or. 2 dice are rolled. Find the probability of getting doubles or a sum of 10. Now you got to ask yourself, can that happen at the same time? Doubles means seeing the same number twice. Can you see the same number twice and have it add to 10? You sure can. So we're going to do the probability of doubles plus the probability that we could have a sum of 10 minus the probability that we have doubles that add to 10. Well, remember, when you roll 2 dice, the total possible sums that you get are 36, because there's 6 numbers on each dice. So the fundamental counting principle would say 6 choices times 6 choices is 36 total sums. So our denominator is 36. Now what are the doubles? 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So the doubles, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So we have 6 ways of getting doubles. Plus, this is still 36 possibilities. Now we're just interested in, well, which ones add to 10. So adding to 10, you could have 4, 6, 6, 4, or 5, 5. So you get 3. So again, you could have 4, 6, 6, 4, or 5, 5. Minus, this is still 36, because the general idea is a sum, so that never changes. But now from our list, what has been repeated? Which answer is in both? Well, 5, 5. It's a double, and it adds to 10. But it's only going to happen one time, right? So we can't count it duplicate times. So we're going to get our answer of 8/36, which reduces to 2/9.